Okay, we're going to be looking at electric potential difference and work. This is prototype 10. As in my previous videos, whenever I ask you a question or ask you to do a calculation, stop the video, try your hand at it, and then continue the video. So let's ask first a couple questions. What is the relationship between electric potential energy difference and the electric field? Of course, that is that the change in electric potential energy is equal to minus Q, the integral E dot ds. What is the relationship between work and the potential energy difference? This comes from your previous semester's studies, and we know that work is equal to the change in potential energy. Now, what is the relationship between work and the change in electric potential? Of course, that is work is equal to minus Q integral E dot ds, which is Q times the electric potential difference, or the charge times the electric potential difference. And we identify the electric potential difference as minus the integral E dot ds. Now, what is the relationship between work and kinetic energy? Okay, of course, work is equal to change in kinetic energy. Now, how are we going to use those relationships to solve the problem posed in 5? An electron, mass 9.1 times 10 to the minus 31 kilograms, with a charge equal to minus 1.6 times 10 to the minus 19th coulombs, negative, starts at rest from point A and has speed 5.0 times 10 to the 6 meters per second at point B. Only electric forces act. What is the electric potential difference? So let's ask the first question. What is the work done on the charge? Once again, this comes from your first semester. Of course, the work is going to be the charge times the change in the electric potential. How is that work related to the change in kinetic energy? Well, remember the work kinetic energy theorem from the first semester. Work is equal to the change in kinetic energy. Now we've identified what does the work, what is the result of the work. How is the change in kinetic energy related to the electric potential difference? And of course, we can write that the change in kinetic energy, which is the work, which we identified in 6, is equal to 1/2 mv final squared minus 1/2 mv initial squared, will be equal to the charge times the electric potential difference. Can we solve for the electric potential difference? Yes, of course we can. Electric potential difference is the change in kinetic energy over Q, and we can write it as shown below. Now let's calculate it. And we calculated delta V is equal to 71 volts. And the final question, relative to the direction from A to B, what direction is the electric field? Does it point from A to B, or does it point from B to A? And of course, and we find that it points from B to A. End of problem.